Welcome back. In this video, we are going to solve problem 14-18 that is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the bending strain energy stored in the simply supported beam subjected to triangular distributed load. EI is constant. So you can see this is a simply supported beam having a triangular distributed loaded. The magnitude here is W0 and here the magnitude is 0. So you have to find the bending strain energy stored in the beam. So let's start with the solution. So as we know that bending strain energy UI is equal to m square dx divided by 2ei, and there is an integral from 0 to whole length L. Now we will find this moment M. So what we will do is that first step is that if you remove this pin support at this point, so you will be having reaction force. Let this point is point A. So this reaction force will be AY, and there is a roller support at this point B. And if you remove this roller support, so there will be reaction force which will be equal to BY. So first we will find this AY and BY by using equation of equilibrium. Now you can see that this is a triangular distributed load. So when it is converted into a point load, so it will be the magnitude will be equal to 1/2 W0 and the length over which it acts. So it will be this one, and that will act at a distance of L by 3 from B side. L by 3, and this distance will be 2L by 3. 2L over 3. Now we'll find this AY and BY by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point B is equal to 0 and taking the counterclockwise moment as positive. So about point B, the first moment will be due to this load 1/2 W0 into L, and the perpendicular distance is L by 3, and this is producing counterclockwise moment, so it will be positive. So I will write 1/2 W0 into L, and perpendicular distance is L by 3. The second moment that is produced due to this AY and perpendicular distance is L about point B, and this is producing clockwise movement, so it will be negative. So I will write minus AY into L, and their sum must be equal to 0. So from here we will get AY into L is equal to W0 L over L square over 6. So from here you will get AY will be equal to W0 L by 6. So this is the reaction force that this pin support applied on this beam. Now we'll find this By by using another equation of equilibrium, that is sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So AY, which is upward, so W0 L over 6 minus this distributed load, triangular distributed load when converted into point load. So 1/2 W0 L plus By is equal to 0. So if you take the LCM, that will give you 6. 6 divided by 6 is 1, and 1 multiplied by W0 into L will be this one. Similarly, 6 divided by 2 is 3. So 3 into minus 1 is minus 3 W0 into L plus By is equal to 0. So from here you can see this By will be equal to 2 W0 L over 6. Or if you further simplify, it will be W0 L over 3. So this is the value of By. Now we have this AY and BY. So what we will do is that we will find moment. So we will cut this beam at any length X. For example, if we cut the beam over this length, for example, if we cut the beam over this length, like this length from this point A is X, clear? And draw the free body diagram. So let me draw it over here. That this is the beam, clear? This is point A where you have AY, and that AY was W0 L over 6. This is the length X where you cut the beam, and when you cut the beam, you will be having a shear force that will be acting this word V, and you will be having a moment M as well. And you can see you have a triangular load as well at this point. Now you can see W0 is the magnitude at this end. So what will be the magnitude at this? So let W is magnitude over here. Now you can see you have two triangles, similar triangle. One is this larger one, and the second one is this smaller one. So by using this ratio, W0 over L, W0 over L is equal to this W over length, which over which it X is X. So from here, this W will be equal to W0 X over L. So at here, the magnitude is W0 X by L. Now, when you convert this triangular load into a point load, so it will be equal to 1/2 the W0 X over L and the length over which it acts, and that is X. And it will act at a distance of X by 3 from this side. So X by 3. Okay. Now let this point is point 1. No, so we'll find this moment by using equation of equilibrium, that sum of all moment about point 1 is equal to 0, taking the counterclockwise moment as positive. So about point 1, the first moment is this counterclockwise moment or reaction moment, which is plus M. So I will write plus M. The second moment due to this load and perpendicular distance is X by 3, and this is also producing counterclockwise moment, so it will be positive. So I will write plus 1/2 W0 X over L into X, and perpendicular distance is X by 3. And the last moment is due to this load into perpendicular distance is X, and this is producing clockwise movement, so it will be negative. So minus W0 L over 6 into X is equal to 0. Okay, so M plus W0 X cube over 6L minus W0 L X over 6 is equal to 0. So you can take the LCM. So this is 6L, and that will give you W naught X cube minus W naught L X is equal to 0. So this moment will become equal to minus W naught X cube plus W naught Lx over 6L. And when you take this W naught common, so W naught over 6L is common. So you will get here is W minus X cube plus Lx. Lx. Okay, Lx. Okay, this is when you divide this by 6 will be L, and that will give you square. So it is W naught L square X. So here I will have L square X. Now you can also write it, the moment equation is W naught over 6L, and that will be equal to L square X minus X cube. So this is the moment equation. Okay. Now we will use this moment equation in this equation in order to find the bending strain energy. So let's move. We know that bending strain energy is equal to integral of 0 to L m square dx divided by 2EI. So just put the value of moment over here. So moment is W naught over 6L into L square X minus X cube. And we will take the square into dx divided by 2EI. Okay. So integral of 0 to L, it will be W naught over 36 L square into L square X minus X cube whole square into dx divided by 2EI. So when 2EI multiply with 36, we will take constant outside. So it will be 32 L square, 72 L square EI, and we will left with integral of 0 to L, L square X minus X cube whole square dx. Okay. Now further simplified. So W naught, okay, this is W naught, this will be W naught square. Okay. Because you are taking the square. Okay. Okay. So W naught square over 72 EI L square integral of 0 to L. Now the square of this will be equal to L4 X square, clear, plus X6 minus 2 times this term into this term. So that will give you 2L square X power 4 into dx. Okay. Further simplify W naught square over 72 EI into L square into integral of this term. So integral of L4X square will be L4 X cube over 3 plus integral of X power 6 is X7 divided by 7 minus 2 L square X5 over 5, and limit will be from 0 to L. That will give you strain energy due to bending. So W naught square over 72 EI L square. Now if you put the limit L, so it will be L4 into L power 3 divided by 3 plus L7 over 7 minus 2 L square L5 over 5. Okay. So further simplify W naught square over 72 EI L square, and that will give you L7 over 3 plus L7 over 7 minus 2 L7 over 5. That will give you strain energy due to bending. And when you solve all these, you will get at the end strain energy due to bending in the simply supported beam comes out to be W naught square L5 over 945 EI, which is the answer of this question. So this is the amount of strain energy that will be stored in this simply supported beam due to bending. And that was all about problem 14-18. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. Also share my channel with your friends and help them in learning as well as and help me in growing my channel further. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 14-20 that is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the concrete column consists 6 1-inch diameter steel reinforcing rod. If the column supports a load of 300 kips, determine the strain energy in the column. E of steel is 29 into 10 to the power 3 ksi, while E of concrete is 3.6 into 10 to the power 3 ksi. So you can see this is the concrete column that consists of 6 this 1-inch steel rod, and the load that it supports is 300 kips. So you have to find the strain energy in this column. So let's start with the solution. So first step is that if you cut this column and draw the free body diagram. So let me draw it first. That this is the frontal view of this column. There is a load of 300 axial load which is acting 300 kips. Clear? And you can see that this load is acting on this concrete column. So some of load is taken by concrete and some of the load is taken by this steel reinforcing rod. So I will write as a result this load will be equal to P of concrete and some of the load is taken by P of steel. So we will apply equilibrium condition in order to write the equation. So this is the equation that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see minus 300, which is downward, plus P of concrete plus P of steel is equal to 0. So from here we can say that P of concrete plus P of steel is equal to 300. Means that this 300 Gibbs load is taken, some of portion is taken by concrete while some is taken by this steel rod. So this is your equation number 1. Now you can see that due to this load there will be deformation in this concrete as well as in this steel rod. Since both are same, both are joined with each other, so their deflection will be same. So we will write compatibility equation. So compatibility equation, which is equal to change in length of concrete is equal to change in length of steel. Okay, as we know that change in length is equal to P into L divided by AE, that this change in length is due to axial load. Clear? So for concrete I will write P of concrete into length, both lengths are same, divided by, I will write it, length of concrete is equal to length of steel, and that is equal to L, divided by area of concrete into E of concrete, that will be equal to P of steel into L of steel, which is equal to L divided by area of steel into modulus of elasticity of steel. So you can see this L will cancel with each other, so we will left with P of concrete divided by area of concrete into EC is equal to PS divided by AS into ES. Now we will calculate this area of concrete. So area of concrete, you can see this is the area. The diameter is given, the radius is given as 12 inch. So radius of concrete is given as 12 inch. Clear? So there are six 1 inch diameter steel rods. So this area of concrete will be equal to this minus the area of this 6 steel rods. So I will write area of concrete is pi r square, RC square, minus 6 times the area of steel rod. So area of steel rod is 6 multiplied by pi r s square. Clear? Now what is this? So pi, area of radius of concrete is given as 12. So pi 12 square minus 6 times pi. What is diameter of steel rod is given as 1 inch. So radius will be 0.5. So 0.5 square. So this is the area of concrete. Now area of steel is equal to pi r square, pi rs square. So that is equal to pi multiplied by 0.5 square. Since there are 6 rods, so I will multiply by 6 multiplied by on both sides. Clear? So now you can put the value P of concrete divided by area of concrete is pi into 12 square minus 6 times pi into 0.5 square. Multiply by E of steel, E of concrete, which is 3.6 into 10 to the power 3. So 3.6 into 10 to the power 3. That will be equal to P of steel divided by area of steel is 6 into pi into 0.5 square. And what about EE of steel is also given as 29 into 10 to the power 3 KSI. So I will write 29 into 10 to the power 3 KSI. Okay, so when you solve this, P of concrete will be equal to 11.7931 P of steel. Yeah, that this is your equation number 2. Now put the value of P of concrete in equation number 1. So put equation 2 in equation 1. So P of concrete is 11.7931 PS plus PS is equal to 300. What I did is that I replaced P of concrete with its value and P of steel was there. So their sum must be equal to 300. Okay. Now when you solve this, it will be, from here you will get P of steel will be equal to 23.45 kip. So out of 300 kip steels, each steel rod takes 23.45 kips load. This is equation number 3. Now put equation 3 in equation 2. So P of concrete is equal to 11.7931 into P of steel, so which is 23.45 kip. And you will get P of concrete will be equal to 276.55 kip. Okay, so it means that concrete is taking 276.55 kip load, while the 6 steel rods are taking 23.45 kips load. Now you have all the loads, so we will find the strain energy due to axial loading, that is equal to sum of N square L divided by 2AE R. We have written here P, so it will be equal to sum of P square L divided by 2AE. So just put the values. So I will write it for P of concrete square into length divided by area of concrete into EC plus P square of steel into L divided by 2 times E of area of steel. So there are 6 steel, so I will write 6 multiplied by AS into E of steel. Now put the value, so you will get U strain energy due to axial loading will be equal to P of concrete is 276.55 square multiplied by length. We will check the length. Length is 5 feet. So in inch, it will be 60 inch. 12 into 5. We'll convert it into inch. 2 multiplied by area of concrete, which is again this one. Clear? So I will write it pi into 12 square minus 6 multiplied by pi into 0.5 square into E of C, which is 3.6 into 10 to the power 3, plus P of steel, which was 23.45 into length is 5 feet, so 5 into 12 will give you in inch, divided by 2, and area of steel, 6 steel rod is this one, so 6 multiplied by pi into 0.5 square multiplied by E of steel, which was 29 into 10 to the power 3 KSI. So when you solve this, you will get strain energy due to this axial loading will come out to be 1.544 kips into inch. And if you want to convert it into feet, you have to divide it by 12. So you will get 0.129 kip into feet. And this, which is the answer of our this question. And that was all about this problem 14-20. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help me in growing further. Thank you for watching. Welcome back. In this video, we are going to solve problem 14-21 that is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is a load of 5 kilonewton is applied to the center of A992 steel beam for which moment of inertia is 4.5 into 10 to the power 6 millimeter power 4. If beam is supported by 2 springs, each having stiffness of K 8 meganewton per meter, determine the strain energy in each of the spring and the bending strain energy in this beam. So you can see this is the beam that is supported on this 2 spring having stiffness K is 8 meganewton per meter, and there is a 5 kilonewton load applied at the mid. So due to this load, you have to determine the strain energy in the beam due to bending and the strain energy in each of the springs. So let's start with the solution. So first we know that strain energy due to bending is equal to integral of m square dx divided by 2ei, and limit will be from 0 to L. So we'll find the moment for this, but before moment, if you remove this spring K, so this spring will exert a vertical reaction on this, which will be equal to P of spring. And similarly, if you remove this spring will exert vertical reaction on this beam, which is also PS. Like this is your point 1 and this is your point 2. So we'll find this PS by using this by using equation of equilibrium. Both spring are same and same stiffness. So PS is equal to, let PS is equal to P. Clear? So we'll find this by using equation of equilibrium that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see P of steel plus P of steel, spring, sorry, not steel, minus 5 is equal to 0. So 2 times P of spring is equal to 5, and P of spring will be equal to 5 divided by 2, which gives you force exerted by spring on this beam will be equal to 2.5 kilonewton. So each spring exert 2.5 kilonewton on this beam. Now what we will do is that we will cut this beam at any length. For example, this length is x, and we will draw the free body diagram to find the equation of movement. So you can see here this is 2.5 kilonewton, this is your point 1, 2.5, and kilo is 10 to the power 3 newton. This is the total length x. Clear? And when you cut it, you will be having a shear force and you will be having a moment as well. That this is point O. Clear? So we'll find this moment by using equation of equilibrium that sum of all moment about point O is equal to 0 and taking the counterclockwise moment as positive. So about point O, one moment is this counterclockwise, which is reaction moment, so it is plus. And the second moment is due to this load 2.5 kilonewton and perpendicular distance is x, and this is producing clockwise, so it will be negative. So minus 2.5 into 10 to the power 3 times x is equal to 0. So it means that moment is equal to 2.5 into 10 to the power 3 times x. Clear? So this is the moment equation. But here x will be for x is greater or equal to 0 and less or equal to 3 meter. Why? Because at 3 meter you can see you have 5 kilonewton load. So what we will do is that we will take one half portion is this one and another half portion this one. Now we will apply this equation. So here you can see strain energy due to bending for this condition, for this loading, or this loading x greater than 0 and less or equal to 3. Here you can see you have two portion. One is this one and another one is for this one. So I will write 2 multiply by integral of 0 to L m square dx divided by 2ei. Okay, so you can just put the value 2 into integral of 0 to L. M value of m is 2.5 into 10 to the power 3 times x square dx divided by 2ei. Clear? So 2 will cancel with this, so we will left with 1 over EI, and that will be from 0 to L 2.5 into 10 to the power 3 whole square into x square dx. So you can take this constant out of the integral, so you will get 2.5 into 10 to the power 3 whole square divided by EI, and you will left with integral from 0 to L, and here this will be equal to from 0 to 3, and we have x square into dx. So if you further simplify, this will be the same EI, and we will get integral x cube divided by 3, and limit will be from 0 to 3. Okay, now you can put the limits divided by EI into x is 3 cube, so 3 cube minus 0 cube divided by 3. And if you put the value of I is also given. You can see the value of I is 4.5 into 10 to the power minus 6. Given is that, so you have to convert it into meter power 4. So that will be 4.5 into 10 to the power minus 6. So I will write 2.5 into 10 to the power 3 whole square divided by I value was 4.5 into 10 to the power minus 6 multiplied by 3 cube divided by 3. And what about E? E for A992. So you have to go to the property table in the book. So here I have mentioned in the yellow color, you can see this is average mechanical property of material, and from yellow this is 200 gigapascal. So you have to write this from here. So 200 into 10 to the power 9 Pascal. This will be the strain energy due to bending. And when you solve this, you will get the strain energy due to bending will come out to be 62.5 joules. So this is the answer of our first part, which is to determine the bending strain energy in the beam. Now we'll find the bending strain energy in the spring. So you can see this load, the spring applies a load on this beam. As a result, this beam will also apply the same force on the spring, that is compression. So we know that P of spring is equal to 2.5 kilonewton. Stiffness of spring is given as 8 meganewton per meter, which is equal to 8 into 10 to the power 6 newton per meter. So we know that deflection in spring is equal to P of spring divided by K of spring, because P of spring is equal to K of spring into deflection of spring. So from here we will get this equation. So now put the value 2.5 into 10 to the power 3 divided by 8 into 10 to the power 6. That will give you 0.3125 into 10 to the power minus 3, and unit will be meter. So this will be the deflection of spring. Now strain energy due to in spring is equal to, as the spring is in compression, so strain energy in spring due to compression will be equal to 1 over 2. This is the formula K into deflection of spring square. So just put the value, you will get strain energy in spring due to compression will be equal to 1 over 2. K is 8 into 10 to the power 6 multiplied by 0.3125 into 10 to the power minus 3 whole square. So when you multiply this, you will get 0.391 joule, which is the strain energy in spring due to compression. So this is the amount of strain energy that will be stored in each spring due to applied loading on the beam. And that was all about this simple problem 14-21. I hope you have enjoyed this video and you are learning from my videos as well. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. Also share my videos in your circle and help me in growing further, as well as help other people in learning. Thank you for watching. Welcome back to another episode that is about problem number 14-22. This problem is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement of this problem is determine the bending strain energy in the beam and the axial strain energy in each of two posts. All the members are made up of aluminum having a square cross section 50 mm by 50 mm. Assume the post only support vertical axial load. Modulus of elasticity of aluminum is 70 gigapascal. So you can see this is the beam and the loading is shown. There is a distributed load of 8 kilonewton per meter, and there are two vertical posts that support this beam. So you have to find the bending strain energy in this beam and axial strain energy in this vertical post. So this vertical post offer only vertical reaction. So let's start with the solution. So what if we remove this post, two posts? So this will apply a vertical reaction on this beam. Like this is the beam. You can see this is the load that due to this post. So this is P of that the load that this post apply on the beam is P of post, and similarly on other side the same length or same material post is applying a load P of post on this beam. There is a uniformly distributed load on this beam which is given as 8 kilonewton per meter there, and this load is downward. So we will find this P of post by using equation of equilibrium. So what will be the equation of equilibrium? So first step is that we will convert this distributed load into a point load. So this will be equal to 8 kilonewton per meter multiplied by the length, and the total length of this beam is given as 3 meter. I will multiply it with 3. So this 3 meter. So this will give you 24 kilonewton load. And that will act at a distance of 3 divided by 2, which is 1.5 meter from either side. Clear? Okay. Now we will apply equation of equilibrium. So you can see the sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So P of post plus P of post. P of post is the load that this post apply on this beam. Minus 24 is equal to 0. So 2 times P of post is equal to 24. So it means that P of each post apply a 12 kilonewton load on this beam. Clear? Now we will move further, and what we will do is that we will cut this beam at any length x. Clear? And we will draw the free body diagram in order to find the equation for movement. So look, you can see this is the beam. Here we have one load P of post, which is equal to 12 into 10 to the power 3 Newton. Clear? And this total length of the beam where we cut it is x. And there is a uniformly distributed load on this, which is 8 kilonewton per meter. So when you cut it, you will be having a shear force and you will be having a moment. This is your point 1. So what we will do is that we will convert first this distributed load into a point load. So this will be equal to 8 multiplied by 8 kilonewton. So 8 into 10 to the power 3 multiplied by this length x, for which it acts. And this will act at a distance of x by 2 from either side. So this distance will be x by 2. Now we'll find this moment by using equation of equilibrium, that sum of all moment about point 1 is equal to 0 and taking the counterclockwise moment as positive. So about point 1, one moment is this reaction moment, which is counterclockwise, and that will be plus. The second moment will be due to this 8 into 10 to the power 3 into x, and the perpendicular distance is x by 2, and this is also counterclockwise, so it will be positive. So plus 8 into 10 to the power 3x multiplied by x by 2. And the last moment that is produced due to this load and perpendicular distance is x, and this is producing clockwise, so it will be negative. So I will write minus 12 into 10 to the power 3x is equal to 0. So what I will get is m plus 4 into 10 to the power 3x square minus 12 into 10 to the power 3x is equal to 0. So if you further simplify it, this moment will be equal to 12 into 10 to the power 3x minus 4 into 10 to the power 3x square. And its unit will be Newton into meter. Okay, now this is the equation of movement. So we will move toward finding the bending strain energy due to bending, and we know that this is equal to integral from 0 to L m square dx divided by 2ei. Okay, so put the value integral 0 to L m square is 12 into 10 to the power 3x minus 4 into 10 to the power 3x square whole square into dx divided by 2ei. That is strain energy due to bending. Okay, now if you take this 1 over 2ei out of this integral, because these are constant, so you will left with 0 to L. So 12 into 10 to the power 3 square will be 144 into 10 to the power 6 x square minus plus 4 into 10 to the power 6 10 to the power 3 will be 16 into 10 to the power 6 x power 4 minus 2 times this term multiplied by this term will give you, I will directly write it, this will give you minus 96 into 10 to the power 6 x cube into dx. That will be equal to strain energy due to bending. Okay, again this bending strain energy will be equal to 1 over 2ei, and what we will take is integral. So 144 into 10 to the power 6 x cube over 3, and limit will be from 0 to L, plus 16 into 10 to the power 6 x5 divided by 5, and limit from 0 to L, minus 96 into 10 to the power 6 into x power 4 divided by 4, and limit from 0 to L. Okay, and you can see x start from 0 to x is equal to L, 3 meter, not L3. Total length is 3. So what is that? I will remove this and I will write it 3. Okay, now we will find E of steel is given as 70 gigapascal, and it is given that this is square cross section 50 by 50. So the square cross section is this one. This is 50 millimeter, and the height is also 50 millimeter. Clear? So moment of inertia is equal to 1 over 12 bh cube. So 1 over 12, breadth is 50, and millimeter in meter it is 0.05, and height is also 50, which is 0.05 meter whole cube. So when you calculate it, you will get 0.52083 into 10 to the power minus 6 meter power 4. Now you have all the values, so you can just put it 1 over 2 multiplied by E is 70 gigapascal, 70 into 10 to the power 9 multiplied by 0.520 into 10 to the power minus 6 multiplied by all these values. 144 into 10 to the power 6 divided by 3x cube plus 16 into 10 to the power 6 x5 divided by 5. Limit will be from 0 to 3. Here limit from 0 to 3 plus minus 96 into 10 to the power 6 x4 divided by 4. Limit from 0 to 3. Okay. So when you solve this, you will get 1777 joules, or that is equal to 1.78 kilojoule. So this is the amount of bending, this is the amount of strain energy that will be stored in the beam due to bending. Now what we will do is that we will find the axial strain energy. Axial strain energy. Let me write it here. This is bending strain energy. Okay. For axial strain energy, we know that strain energy due to axial loading is equal to integral of 0 to L n square dx divided by 2 AE. Clear? So what we will do is that we have n is actually the normal load or axial load. So you can see the axial load of this post is PS 12 kilonewton. This beam is applied 12 kilonewton load on this post. So I will write from 0 to L 12 kilonewton. So 12, and that is also equal to, since it is equal to n square L divided by 2 AE. Okay. So 12 into 10 to the power 3 whole square. I will remove these things because this is already, we know that axial strain energy is equal to normal load square into L divided by 2 AE. So if you write this or this, both will give you the same thing. And length of each post is 1.5 meter. So 1.5 divided by 2 times area. Area of this cross section is given. So area is 0.05 multiplied by 0.05. And E is 70 gigapascal, 70 to 10 to the power 9. That is due to axial loading. So when you calculate it, you will get strain energy due to axial loading will comes out to be 0.617 joule. So this is the amount of strain energy that will be stored in each of the post. Clear? And that was all about this problem 14-22. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help them in learning, as well as help me in growing my channel further. Thank you for watching and thank you for your support. Welcome back. In this video, we are going to solve problem 14-146 that is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the total axial and bending strain energy in A992 steel beam. Area is 2300 square millimeter and I is 9.5 into 10 to the power 6 millimeter power 4. So you can see this is the beam. There is a pin support at this point, clear, and there is a roller support at this point. The horizontal force is 15 kilonewton and there is a distributed load of 15 kilonewton per meter or a length of 10 meter. So you have to determine the total axial and bending strain energy. So we'll find the axial strain energy and we'll find the bending strain energy, and then we will sum these two to get the total strain energy due to bending and axial. So let's start with the solution. So first step is that if you remove this roller support, so you will be having a reaction force. Let this will be reaction force will be R. Let this is your point 2, so it will be R2 Y. And this support, pin support, is the point here is 1. So if you remove this pin support, so you will be having a vertical reaction force which is equal to R1Y, and there will be horizontal reaction which will be R1X. So we'll find this R1X, R1Y, and R2Y by using the equation of equilibrium. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0, and force in this direction is taken as positive. So you can see one force which is 15 kilonewton is in positive direction, and the second one is R1x, that is in negative direction. Their sum must be equal to 0. So I will write 15 minus R1x is equal to 0. So from here you will get R1x will be equal to 15 kilonewton. Now we'll find in another reaction R1y and R2y by using equation of equilibrium, that sum of all moment about point 1 is equal to 0, and taking the counterclockwise moment as positive. So you can see there is a distributed load when converted into point load, so it will be act at the middle of this beam, and the magnitude of this point load will be 1.5 into perpendicular distance is 10, and that will be equal to 15 kilonewton, and that will act at a half of this total length, which is 5 meter, okay, on either side. So this will be 5 meter and this will be also 5 meter. Now apply this equation. So about this point 1, the one moment will be 15 kilonewton into perpendicular distance is 5, and that is producing clockwise moment, so it will be negative. So I will write 15 into 5, and that is minus. The second moment is due to this R2y, and perpendicular distance is 10, and this is producing counterclockwise moment, so it will be positive. So I will write R2y into 10 is equal to 0. So what we will get is minus 75 plus 10 R2y is equal to 0. So from here you will get 10 R2y is equal to 75, and when you divide 10 on both sides, so you will get R2y will be equal to 7.5 kilonewton. Now you have R2y So you can also get R1y by using equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see one force is R1y and plus R2y minus 15 will be equal to 0. So R1y is not known, plus R2y is 7.5 minus 15 is equal to 0. So again from here you will get R1y will be also equal to 7.5 kilo Newton. Now you have all these forces. So what we are going to do is that we will take any section in the beam. So you can either take x in this direction or x in this direction. Both will give you the same thing. So what we are going to do is that we will cut the beam over here and we will take the distance x from this. So this will be, and we will draw the free body diagram. So let me draw the free body diagram. That this is the beam. Clear? So you can see at this point we have 15 kilonewton load, axial load 15 kilonewton. At this point, this is your point 2. At this point you have vertical force which is R2y, that is 7.5 kilonewton. Clear? The total length of this beam where we have cut it is x. So this is x. And when you cut it, so you will be having a shear force V and you will be having a moment. Clear? So moment will be like this. Okay. This will be the moment. And you can see you have a distributed load over this beam and this load is 1.5 kilonewton per meter. So when converted into a point load, so it will be equal to 1.5 multiplied by x, and it will act at a distance of x by 2 from either side. So this distance will be x by 2. Now this is point O, so we'll apply equation of equilibrium. So what will be the equation of equilibrium is that sum of all moments about point O is equal to 0 and taking the counterclockwise moment as positive. Now remember that there is also a normal force that will act in this direction n. Clear? So we'll find this n as well. Clear? So we will apply first this equation of equilibrium. Sum of all moment about point O is equal to 0. So about point O, one moment is this clockwise moment which is minus m. So I will write minus m. The other moment that is produced due to this 1.5 x and perpendicular distance is x by 2, and this is also producing clockwise, so it will be negative. So I will write minus 1.5 x into x by 2. And the last force that is producing moment about point O is this 7.5 and perpendicular distance is x, and this is producing counterclockwise moment, so it will be positive. So I will write plus 7.5 times x is equal to 0. So from here you will get this moment will be equal to 7.5 x plus minus 1.5 x square over 2. Okay, so what we are going to do is that you can see this force is in kilonewton, so you can also convert it into newton. So 7.5 into 10 to the power 3x minus 1.5 into 10 to the power 3 and x square over 2. So you can also take it, or you can use this one or this one. Okay, now what we are going to do is that we have find this moment. Clear? So we are going to find the horizontal force as well. So horizontal force can be obtained by using equation of equilibrium, that sum of all forces along x direction must be equal to 0 and force in this direction is taken as positive. So we will need only this n is minus n plus 15 is equal to 0. So from here n will be equal to 15 kilo Newton. Now you can see you have a normal this axial load as well as you have moment. So first what we will do is that we will find the axial strain energy. So axial strain energy, I will write it for axial load. For axial load, we have strain energy axial is equal to integral of 0 to L n square dx divided by 2ae, or this is also equal to, for single load it is n square L divided by 2ae. Clear? So you have all the values. N is 15 kilonewton, so 15 into 10 to the power 3 square. What about length of beam? Length of beam is 10 meter. So I will write multiply by 10 divide by 2 times area. Area in meter is given as, it is given in millimeter. So when you convert it into meter, it is 2300 into 10 to the power minus 6. So 2300 into 10 to the power minus 6 multiply by E. E is not available. So what we will do is that we will go to the property tables and we'll find A992 steel. So here you can see that this is A992 steel and E value is 200 gigapascal. So note down this value 200 gigapascal. So I will write here 200 into 10 to the power 9 value. So when you solve this, you will get strain energy due to axial loading comes out to be 2.4456 joule. Okay, so this is the strain energy due to axial loading. Now what we will do is that we will find for bending. So for bending, we know that strain energy due to bending is equal to integral from 0 to L m square dx divided by 2 ei. or this can be written as, if you take 1 over 2e outside, so you will be having integral from 0 to L m square dx. Now you have the value of m, so you can just put it in that. M is this one here, so you can put 7.5 into 10 to the power 3 x minus 1 over 1.5 divided by 2 is 0.75 x square whole square into dx. Okay, now what you are going to do is that you will take the square, so strain energy due to bending is equal to 1 over 2ei integral from 0 to L 7.5 square. 7.5 into 10 to the power 6 square will be 56.25 into 10 to the power 6 x square plus 0.75 whole square will give you 1 square will give you 562.5 into 10 to the power 3 x power 4 minus 2 times this term plus this term will give you minus 11.25 into 10 to the power 6 x cube into dx. Clear? Now you can take integral and you can take the limit. So integral of this 56.25 into 10 to the power 6 x cube over 3 and limit from 0 to L plus 562.5 into 10 to the power 3 into x power 5 divided by 5 and 0 to L plus minus 11.25 into 10 to the power 6 x power 4 divided by 4 and limit from 0 to L. As you can see, x start from 0 to x is equal to 10. So what we are going to do is that we will remove this L and we will write it over here 10. Okay, now when you put all the values, okay, 1 over 2e is 200 gigapascal, so 200 into 10 to the power 9, and I is also available, which is 9.5 into 10 to the power minus 6. 9.5 into 10 to the power minus 6 multiply by 56.25 into 10 to the power 6 divided by 3 multiply by 10 minus 0 whole cube plus 562.5 into 10 to the power 3 divided by 5 into 10 minus 0 whole power 5 minus 11.25 into 10 to the power 6 over 4 into 10 minus 0 power 4. This will give you bending strain energy. Okay, and again when you solve all this, at last you will get the bending strain energy UBI will be equal to 493.2 joules. Now you have both this clear. Since we have been asked to find the total strain energy, so total strain energy will be equal to strain energy due to axial loading plus strain energy due to bending. So put the value 2.4456 plus 493.2 joules, and when you add these two, so what you will get is that you will get 496 joule, which is the answer of our this question. So this was all about this problem 14-146. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help me in growing my channel further. Thank you for watching.